Dear friends, welcome to Infos. Welcome to another oil and gas training video. We are continuing our videos on valves. So this time valve part number 10. In this video we are discussing about pneumatic actuators. Some of the actuators we have already discussed in part 9. Manual operation also, manual valve also. So in this time we are control valve actuators, general actuators principle, construction, advantage and disadvantages, different type of actuators, etc. We are discussing in this video. Welcome to this video. Number one is diaphragm actuators. The most commonly applied pneumatic actuator over the past 40 years has been diaphragm actuators. Most diaphragm actuators are designed for linear motion, although some rotary motion design exists. You can see here, this area is the actuator, diaphragm is coming, below that one spring is there. Some constructional details are providing in this picture. A typical diaphragm actuator is a single acting actuator that provides air pressure to one side here, side of an elastomeric barrier called diaphragm, here the diaphragm, to extend or retract the actuator stem to move up and down, simply speaking, which is connected to the closure element. In the bottom area is connected to the closure element. The diaphragm is sandwiched between upper and lower casings, either on which can be used to hold air pressure depending on the style of the actuator. So either from air pushing from here or air lifting the diaphragm from here, both we are discussing now. The coming slides we will discuss that one. So different type of actuators are there. With the conventional single acting diaphragm actuators, the air signal from the controller to the actuator has a dual role. First, it provides positioning the signal. In our previous many classes, we are talking about positioner. Hopefully in our next video will be on positioner. So the signal, air signal or control signal coming from the controller is going to positioner. Then it is positioning the signal proportional to the power applied to the diaphragm actuator. Then it is releasing the signal to equivalent signal to diaphragm. So that is what is telling. It provides positioning the signal. Second, it provides the power to generate the thrust necessary to overcome the process forces, friction, gravity, the weight of the closure element, and opposing force generated by the range spring. So this coming from the positioner output, and the positioner input is from the control signal. Already in many cases, many places in process instrumentation side, control valve side, we have already discussed that one. If you didn't watch that videos, have a look that one, reverse that one, you will understand a clear understanding on that if you are have a look on that. Diaphragm actuators have both direct acting and reverse acting designs. Two type of designs are there, both are here, I will explain. With the direct acting design, air pressure is sent to the actuator, which extend to the actuator stem and allow the valve close here. Direct acting. Here, air is pushing from the top to bottom. So it is pushing to close. So in other case, air is to close, or no air mean it will go its normal position as open. There is, I have discussed the fail to open, fail to close valve in one of my control valve session in previously. This is regarding that one, fail to open valve, this one, air is pushing from the top. And diaphragm is also near top of the actuator system. And in reverse acting, look at that one, air is from here, it is lifting. So normally a valve is closed. No air mean valve is closed and the air is lifting the valve. So air to open valve or fail to close valve. This also means that the actuator will retract stem upon the loss of air. So it will go back, allowing the valve open and remain open. If no air is there, this valve is remain open. This valve is remain closed. Where the reverse acting design, as their air pressure sent to the actuator here, the stem retract to the valve open. Normally it is closed. If the supply or air signal pressure interrupted, the actuator move to the extended position, allowing the valve to close. So both direct acting and reverse acting, or the control safety issue concern for the safety, it is providing some abnormal activities in case air fail, electrical fail, or any ESD activated, this valve will go to its normal position, fail to open or fail to close. With the direct acting design, air is introduced from the upper casing located above the diaphragm here. Air is introduced into the upper casing and pressure build the diaphragm and plate push against the spring. So it is air is from here and pushing the spring down, direct acting. The movement allows the actuator stem to extend and the valve move toward closing position in direct acting. Eventually, as the full signal air pressure is reached and the resulting air pressure is introduced into the chamber, the diaphragm and plate reach its full travel. That means it's fully open. When the reverse acting design, the lower chamber is provided air pressure and here from the bottom retract to the actuator stem, where a reverse acting spring is used to provide counter force as well as in the failure mode. So here it is like that one. It is entering from here. The upper casing is a static. Here the upper casing is a static and only needs to retain diaphragm to vent displaced air volume to atmosphere. As the actuator stem retracts, the valve begin to open and continue while moving to more open position. When it is retract moving upside, valve will move open and open, more open. When the signal changes and or reducing the signal and no signal, moving lower end of the range, valve start toward closing position. The chief advantage of diaphragm actuators is that they are relatively inexpensive to produce and are commonly seen through the entire process industry. These are the different picture. Here is also one more. Although limited in high thrust requirements, they are well suited to a good portion of application in lower pressure ranges where thrust requirements are not demanding. Generally, diaphragm actuators are ideal for those applications in which precise positioning and immediate response are important and in which medium the low thrust is acceptable to overcome the process and valve forces. So these are the some advantages of diaphragm actuators. Some disadvantages as well, because of the diaphragm is relatively large. The subsequently large casing may present weight and height problem, especially when mounted on a smaller valve size. That is the one disadvantage. This can cause problem with stress at a connection point between a small valve and oversized actuator. Generally, diaphragm actuators, because of the limitation of the diaphragm, do not provide exceptional stiffness and therefore have problem with the fluctuation in the process flow. Another disadvantage in the process flow. From a maintenance standpoint, the life of diaphragm actuators is somewhat limited by the life of the diaphragm. If the diaphragm develops even a minor failure, the actuator is inoperable. This is also another disadvantage. So another commonly using actuator is a piston cylinder actuator. Let us see what are the constructional definition, importance, or that one, how it is working, and advantages and disadvantages, if any. Let us see that. So this is the piston cylinder actuator. Although the diaphragm actuator is most common pneumatic actuator, compressed air is using, The piston cylinder actuator is gaining widespread acceptance, especially as process become more advanced and demanding. The piston cylinder actuator, here it is there, uses a sliding sealed plate called a piston. It is here inside a pressure retaining cylinder here to provide double acting operation. With a double acting design, air is supplied from both sides of the piston by a positioner. As with all double acting actuators, a positioner must be used here. This is the positioner. We are going to take a detailed session in coming video about the positioner. So I am not explaining in detail here. So a positioner must be used to take the pneumatic or electronic or electric signal from the controller and send the air to one side of the piston while bleeding the opposite side until the correction position is reached. So the output is, this output is going to the piston, or either or this output or this output, both it is going, and the control signal is also entering from one side, and pneumatic air is equivalent air supply is entering from another area. Like diaphragm actuators, piston cylinder actuators can be used either linear or rotary valve, both valve possible, this piston cylinder actuators. Linear designs are most efficient since the entire movement of the actuator stem is transferred directly to valve stem. Linear design are most efficient. On the other hand, the rotary design must be some type of linear to rotary motion linkage. This can create some hysteresis and dead band because of the lost motion caused by the use of linkages or slotted levers. The body of the linear cylinder actuator involves a cast yoke which is used to make the connection to the valve body. It also provides a room for the connection between the valve stem and actuator stem, attaches the cylinder mechanism to the valve, support the actuator stem, and allows the installation of the positioner and other some constructional details. That's all. The cylinder can be made either aluminum or steel based on the application. So different material using for construction. The piston itself is a flat disc that is machined neatly to the inside diameter of the cylinder. Piston cylinder actuators are reversible, meaning the same actuator can be modified to either air to close or air to open. Both it is possible. See, air to close or air to open. Both type application is possible. Both type design is possible. As a general rule, piston cylinder actuators are much more compact, being smaller in height and weight than diaphragm actuators, an important consideration with installation and maintenance. Much more compact, being smaller height in weight than diaphragm actuators. This is a good point for that one. Important consideration. Non-pneumatic actuators, two actuators in pneumatic operating actuators, diaphragm and piston cylinder. Now non-pneumatic, we have electric actuators, motors installed on a process valves, where one of the first type of actuator used in the process industry. This is a electric motor actuator, MOV, motor operator valve, usually mentioning in P&ID. The electric actuator consists a reversible electric motor, control box, gearbox, limit switch, and other controls such as potentiometer to show valve position, like a limit switch. The chief application of electric actuators are in the power and nuclear power industries, where high pressure water system require smooth, stable, and slow valve stroking. These are the inside the control system. A little bit looking complicated. Another one is electric and hydraulic actuators. Hydraulic actuators are use hydraulic fluid and below a piston and position the valve. So hydraulic fluid is using to power the piston. Hydraulic pressure can be supplied by an external plant of hydraulic. A hydraulic tank, oil tank will be there. It is pressurizing and hydraulic fluid is supplying to the piston. In similar is design to a cylindrical actuator with a cylinder and a piston acting a divider between the two chambers. It is almost similar to cylinder actuator design. Hydraulic actuators do not have a failure spring. So, providing a failure action requires a series of tripping systems which are very complex and require special engineering. Normally, all wellhead operating valves, wellhead actuator operating valves are hydraulic for the high safety and high safety concern and precision operation. Normally, position working this using this type of wellhead operation, master control valves and other safety subsurface and surface safety valves are hydraulically operated. An electrohydraulic actuator uses hydraulic actuator, so it is electrohydraulic, uses hydraulic actuator rather than use a external hydraulic system. It has a self-contained hydraulic source that in a physical part of the actuator. Inside itself there is a hydraulic system is there inside. Electrical signal feed to an internal pump which uses hydraulic fluid from a reservoir small tank to feed hydraulic fluid above or below the piston. The chief advantages of hydraulic and electrohydraulic actuators are that are expensive, chief disadvantage, expensive, large, bulky, highly complex and require special engineering. So, next is almost all actuator we have quickly finished. So, number of performance wise number of parameters we are considering for actuator performance. A number of technical terms are used to describe the performance of and capabilities of an actuator. Hysteresis is a common term used to describe the amount of position error that occurs when the position is approached from opposite direction. Repeatability is a similar to hysteresis, although it records the maximum variation of position when the same position is approached from the same direction. Typically, hysteresis and repeatability reading can be anywhere between 0.25 to 2% of the full stroke of the actuator. These are the design parameters, performance parameters, not much on operating parameters. Response level, some of other words are there, is the maximum amount of input change required to create a change in the valve stem position in one direction only. Typically, response levels can be anywhere between 0.1 to 1% of full stroke. Deadband is a term used to describe the maximum amount of input that is required to create a reversal in the movement of the actuator stem. These are the terms which is using mainly it will be benefiting for maintenance people, control system people, instrument people and mechanic, somewhat for mechanical people. Typically, deadband measurements can fall between 0.1 to 1% of the full stroke. Resolution describes smallest change possible in a valve stem position. Typical, it is playing between 0.1 to 1% of the full stroke. Steady state air consumption, that another term is using for the performance monitoring, applies the actuator with positioners in which the positioner consumes a certain amount of air pressure to maintain a required position. Depending on the positioner design, typically steady state air consumption can vary anywhere between 0.2 to 0.4 standard cubic feet per minute, between 1.6 to 3.2 cubic meter cube per minute at 60 psi or 4.1 bar. So, we are ending this video on actuators. We have reviewed pneumatic actuator, electrical and other actuator, non-pneumatic actuator. So, next video is one of the important video in control system and valve application. Control valves mainly a positioner. Positioner is a controller. You can see many things are there. Actuator, this is, we have discussed that one. This area we are going to discuss a positioner and the air signal is there. Valve body is there. We have already discussed the valve, different type of valve. So this is the control signal is coming, air signal is coming, and the air to diaphragm is going by positioner. There are many constructional details, advantages, how it is working. So many things we have to discuss in our next video. So request you to all watch this all valve video to get a continuity that one. Thanks for watching this video. Have a good day.